In this video, we'll be looking at proving trig identities, but specifically trig identities as they're covered in the grade 11 university course. So they're a little easier than some of the grade 12 trig identity videos that I have. And one identity we're going to need, just to prove the ones we're working on today, is that sine squared x plus cos squared x equals 1. That's pretty important for us. So let's look at this first one. We'll set up our left side, right side. On the right hand side there isn't going to be much to do. It's just 1 plus cos x. On the left hand side, however, where most of our work is going to be, we have sine squared on the top and 1 minus cos x on the bottom. Well, the big move here is to notice that sine squared isn't going to help me get closer. I need to get rid of this 1 minus cos x. But using this formula, this identity I just wrote down, if sine squared plus cos squared equals 1, we can move this cos squared to the other side by subtracting it and recognize that sine squared would just be 1 minus cos squared. In other words, sine squared can be replaced by 1 minus cos squared x all over 1 minus cos. That's good because 1 minus cos squared, we can use difference of squares. This is 1 minus a square. So we can rewrite that as 1 minus times 1 plus cos x. And that'll work because it's difference of squares. If you don't believe me, you could rainbow it back in. You'd get 1 times 1 is 1, then plus cos x, then minus cos x, so that plus and minus cos cancel out, and you get minus cos squared. So this is indeed the right expansion, difference of squares, of 1 minus cos squared x. And that's great because now we have 1 minus cos on top, 1 minus cos on the bottom. Since they're being multiplied, we can cancel them out, and we're just left with 1 plus cos x. Since now, upside down therefore means since the left side equals the right side, therefore we've proven this true. Let's look at the second one, similar type thinking. We want to start off by doing left side, right side. We have cos squared x on one side, and on the other side we have 1 minus sine x, 1 plus sine x. There's different ways that you can solve this. I think I'll work both sides to start here. I'll begin with same thinking as we did last time. I want to rewrite cos squared using this formula but rearranged. If sine squared plus cos squared equals 1, I can move this sine squared over and recognize that cos squared would just be 1 minus sine squared. And I could work on that side if I wanted. I think what I'll do, just like I was explaining in the last question, is talk about the idea of foiling this back. So let's get rid of these brackets, 1 minus sine times 1 plus sine, by foiling. That is, first times first. 1 times 1 is just a 1. 1 times plus sine x is plus sine x. And then that's the first two, and now these second ones, the insides, minus sine x times 1 gives you minus sine x. And then minus sine times positive sine will give you minus sine squared. Sine times sine is sine squared, but minus times a plus just gives you a minus. And in the middle here, plus sine x, minus sine x, these cancel out. It's just adding something and subtracting something. Those operations cancel out, and you're left with 1 minus sine squared x. Our goal here was to get the left side equal to the right side, and since, the little symbol means since we've done that, left side equals right side, therefore we've proven the identity true. The third one's going to have a different strategy though here. We have tan x plus 1 over tan x, make sure my fraction covers the whole thing, equals 1 over sine x cos x. So start with left side, right side, divide it up. Tan x plus 1 over tan x. And on the right hand side, 1 over sine cos. Most of my work is going to take place on the left side here. And I'm just going to use this formula that we have, which is tan is the same as sine over cos. That's an important formula for this question, or identity I should say. So tan is the same as sine over cos. And even when it's under the fraction, I'll just put the 1 on top and say tan again is the same as sine over cos. The next step is to remember your rules about fractions, which is when you're dividing, 1 divided by a fraction is the same as multiplying by its flip. So 1 divided by sine squared, 1 divided by sine over cos is the same as 1 times, and now you flip this fraction, cos over sine. And you don't even need that 1 there. Let's get rid of it. This is just sine over cos, and again, I had 1 divided by something, I change it to 1 times its flip, or what that is, when I'm dividing by a fraction, I multiply by its reciprocal. And so now I'm just adding cos x and sine x. Okay, well, we want common denominator here, which is going to work out well for us trying to get to sine and cos on the bottom here. This fraction is out of cos, this fraction is out of sine. So what's missing? What do they need in common? They both need sine and they both need cos. So I'm going to multiply this first fraction by sine and by sine. So on the top I get sine squared, and on the bottom I get sine times cos. That's just sine cos. Whereas the second fraction, let's make that visible, addition sign. On the second fraction, it's cos over sine. I want a common denominator, so it has to have a cos as well. So I'm going to multiply the top by cos and the bottom by cos. Cos times cos on the top gives you cos squared, and on the bottom you get sine times cos. The whole point of common denominator is now that you have a single denominator, you can write this as a single fraction. That is, they're both out of sine and cos, so we can write that as one fraction, and in this case add the numerators, we get sine squared plus cos squared. Well, that's perfect, because from this identity we have up here, sine squared plus cos squared is just equal to 1, and we are left with 1 over sine x cos x, which is what we wanted. Once again, we've shown that since the left side equals the right side, therefore we've proven the identity true. So this was just a few examples of some questions where we're proving trig identities based on the grade 11 functions course.